Hello everyone, this is INE Foundation Lab 2 section 7.2 PEC routing. Okay, before I configure this section, let me explain MPLS concept quickly and I will come back and configure this section. Okay, I have downloaded MPLS cheat sheet from IPVT's website. Let me review this cheat sheet. There is MPLS protocol header. MPLS protocol MPLS label is located between the link layer header and layer 3 header. It is called experimental bit and it is 3 bits. It is also called layer 2.5 because it is between layer 2 and layer 3. It is located between these two layers. Label is 20 bits. Experimental bit is 3 bits. And we have bottom of stack 1 bit and time to leave 8 bits. And this is MPLS router roles, or this is our MPLS network overview. We have C, P, C, and C. This is, let me draw this. Okay. MPLS network is something like this. We have C, P, and P routers. This is customer edge. This is customer and customer edge. This customer network. Then we have P and P in provider network and C in customer network. Here P, if packet is coming from this, let me this coming from this way. P is called label LER, label edge order, or because it is coming this way, this is incoming, right? This called ingress LSR. Don't confuse this ingress LSR by LSR itself. These two are different. This P will become LER or egress LSR. And this will P is LSR itself. Label switch router. Provider router P, C, and C. We have MPLS tables. It is like routing table. In routing table, we have RIB or routing information base table. And then we have FIB or forward information base table. To see this RIB table, we use show IP route, and to see the FIB table, we use show IP safe command. And this LIB and LFIB or LFIB, these are MPLS labels. To see LIB or label information based table, we use show MPLS LDP binding commands, and to see this table, label forward information based table, we use show MPLS forwarding table command. These two tables are for MPLS, and these two are normal routing tables. And this is MPLS tables. Then we have VRF, MPPGP, VPN4. I will expand this VPN4 today in this section. VPN4 96-bit address comprising 64-bit RD and 32-bit IP addresses. This is VPN4 address. It consists of 64-bit root distinguisher RD, and 32-bit or normal IP address. And we have RD, or this is root distinguisher. It is 64-bit value that allows overlapping address space between different customers in MPBGP. And we have root target RT. It is 64-bit. It is 64-bit BGP community used to transfer routes between VRF and VPN. I will explain this RT later in this section. This for root target is for exporting and importing VPN or VRF routes. We have LDP, Label Distinct Protocol, TDP, this is Cisco proprietary, this is open standard, LDP, LSP, LSP, the label switch path, it is part to MPLS network, and the signing protocol is set up as signaling protocols such as LDP. This is fake, forwarding equivalent class, group of packet forwarded some path with same path attribute. In frame relay we have fake either. This is in block frame relay. And we have LSR. There is no LER here, but we have LSR and LER. This is label switch for the LSR determine what label operation. This is LSR is P. Also, this is P provider router. And is troubleshooting and verifying command, show MPLS interface, debug MPLS, show IP VRF interface, show IP root VRF, and show IP BGP VPN before RD value. And show IP BGP VPN. This is BGP at MPBGP address family VPN before. VPN before is another address family for MPBGP, like IPv4 and IPv6. Ping and show IPBGP VPN before command to see this BGP information. Okay, LDP. This is we have LDP, Label Distinct Protocol, enables label switch port LSI in MPLS network to exchange label binding information for supporting upward forwarding in MPLS network. And we know that there is LDP and TDP. Okay, in general, for LDP neighborship or peering, there are two ways for establishing LDP neighborship or peerings. One is basic discovery mechanism, and the other one is extended discovery mechanism. This extended discovery mechanism is for MPLS-TE network or service large service. It is used in large service providers. Extended discovery mechanism is not directly connected neighbors. They are separated. In other words, if the LSI is more than, there are more than one pair away from each other. If the LSI is more than one hop from each neighbor, it is not directly connected. Then it is called extended discovery mechanism. When LSI is more than one hop, it is called extended discovery mechanism. And if LSI is one hop from its neighbor, it is called directive mechanism. Directive mechanism is when LSI is one hop from its neighbor, and extended discovery is when LSI is more than one hop from its neighbor. In here we use directive mechanism. Okay. uh, LDP direct discovery or directly connected, or in other words LSR, when LSR one have a mission event. LDP discovery, it uses UDP port 646 and session and this session is built on TCP port 646. LDP first sends UDP multicast hello packets to discover other neighbors, then builds its neighbor adjacency using TCP connection. It first uses UDP multicast, then it builds neighbor adjacency using TCP connection. Okay, during the discovery phase, hello packets are sent on UDP port 646, and LDP uses multicast address of 224.0.0.2 to send this LDP hello packets to discover other neighbors, and LDP uses UDP port 646 for source and destination, and it uses its local interfaces IP as source. In other words, LDP uses local interface IP as source and destination address of this one to send hello packet, and it uses source and destination on port of 646. This address is called router on its subnet. This is LDP. Okay, we have LDP Router-ID, LSR-ID, and LDP Transport Addresses. Okay, LDP will use Router-ID as the source of TCP session, and for modifying this LDP Router-ID, we use MPLS LDP Router-ID interface command. By default, the router is selected with the highest IP address of loopback, and if there is no loopback, highest IP address activity will be selected. LSR-ID. An LSR-ID is the unique identifier for LSR on the network. It is consists of two components. First, for called LDP Router-ID to identify LSR that owns the label space, and the last part called local label space ID. This is identify the label space within the LSR. Okay, in Cisco world, if we want to set LSR-ID, it is the same as Router-ID command. To configure LSR-ID on Cisco router, we use MPLS LDP Router-ID and interface command. This is to configure LSR-ID. Because there is one packet here, this is packet capture. If we packet capture, it uses UDP LDP uses UDP port 646 for source and destination, and it uses local interface IP address of as source IP. If I where is this picture? Okay, you see source port 646 and destination port is 646, and we have labeled distribution protocol. This is LSR-ID 11111. We can configure this by this command, LDP Router-ID interface command. And then we have IPv4 transport address. Let's check this address. LDP transport address. It is used to establish the TCP connection. It's the source address of LDP messages, and by default it is selected by same. It is selected by the same way as LSA. By default, it is selected based on highest IP address of loopback interface. Highest IP address on the loopback interface. If there is no loopback, then it is selected based on highest address of active physical interface. And to modify this transport address, we simply use MPLS LDP discovery transport address interface command. This is interface. We have to choose. We have to select interface, not our IP address. Same as here. Okay. I have explained this in previous section. Everything same as here. And we have push, label push, swap, and pop. Then we have permanent popping. This is permanent popping. It is removing the outmost label of an MPLS packet by LSR. If I check, it is removing by last LSR, not PE. If this LSR removes this label, it is called permanent popping. It is removing the outmost label of MPLS packet by LSR before the packet is passed to LER. This is called PHP or permanent popping. And it is done with the implicit null label, and it has a value of 3. And to verify, we can use show MPLS LDP binding label command on LSR. In this topology, R3 is LSR. If I do show MPLS LDP bindings, label remote is 10, 10, 10, and 10. This is implicit null. And if I type 999 and 9, it is implicit null label. It is RT is doing PHP instead of popping. And we have range of values. This is we have label number 0. It represents the IPv4 explicit null label. And we have label value of 3. It indicates that the LSR pops the top label. This is about popping and so on. Okay, this was MPLS quick review. Okay, for this section I want to explain this root target. Let me explain this. Okay, in MPLS network and in general MPLS VPNs, or we usually use MPBGP, multiple BGP, and we use address family IPv4 for our BGP section. Okay, we have MPLS root distinguisher and MPLS root targets. MPLS root distinguisher. the ID is used to create 96-bit address. It is called VPN before address. It is located VPN before address. And ID is a unique 64-bit number that is appended to the IP address. IP address is 32, and it is 64-bit plus 32. It is called 96, and it is called IP before IP. It is called VPN before address. VPN 4 equals 64 plus 32 IP address. So 64-bit RD and 30-bit IP. The format used to configure RD. Okay. The format used to configure RD is like this: ASN colon NN. This is we can configure IP address. And it allows P or earlier routers to determine to which customer or particular prefix belongs. And this must be unique for different VRF on the same P or earlier. Let's say what. Okay, for configuring RD, it is we first create our VPN. Our VRF. This is old way creation of VRF, and this is new way creation of VRF. I prefer this one. It supports address families for IPv4 and IPv6. We just type VRF definition, our VRF name, and under this configuration, we simply type RD and specify ASN colon NN. This is for creating to distinguish. And MPLS target. The RT is a 64-bit or 8-byte BGP community used to tag prefixes. It is used to control the distribution of VPN routing information between P orders. And RT acts as a tag for VPN routes, and it is attached to BGP update messages. Okay, we have two types of targets. One is import RT and the other one export RT. Okay, for import RT, when a P router imports VPN routes with an import RT command that match the import RT specified in the VRF table. I will show this in this section. It is so simple. In one side, well, let me clear this. New. This is our topology. Zoom. This is customer edge. This is P or customer edge, and this is a P. We have to see in here we specify import. We import. For example, I want to export. I create. If I want to see if I want to share these two C's and both can see both be able to see each other, I simply export RT here. I create RT as I create export, and for this switch for to able to see this network here, I simply import this RT. Here I export, and other side I import. This is the way these two C router or network can see each other. This is the job of with targets. Or otherwise, I can export here and import here. Okay, this is okay. This is, and we have export VPN rules by attaching an export RT to them. This is the job of with target. To allow which C network can see each other, or distribution of VPN routing between P routers. Okay, one other thing I want to remind is OSPF type 5 LSA. It flies into other network and being generated by ASPR. We have E1 and O2, E2 entities. This is one important to understand. If you create different OSPF process ID on the same router, this each process will have its own separate link state databases and routing table, and they will not share any information with each other unless you explicitly dispute route between them. Okay, if I explain one of these. Okay, if I create different OSPF process ID on router 3, let's create router OSPF process ID of, for example, 1, and router OSPF process ID of 2. Then I have to redistribute these two OSPF so that each other can see, so that each so that its own network can see each other's. Distribute, and this will become LSA type 5. It means that each process will treat the other process as an external source, and it will generate LSA type 5 as external LSA to advertise routes learning from each other processes. This is okay. Let's configure. This section. Okay, this is there is CE here. We have CE. We have CE. This is provider edge or ingress. I said earlier, I don't call it egress or ingress. This is PE earlier, and we have PO LSR here. Okay, configure a new link between R9 and switch T with IP address of this and use VLAN 200. Okay, well, I have to make sure that we have VLAN 200 in our network. Oops. Uh, Let's show the physical. This is our logical view of our topology. This is our physical view. Our router attached to switch 1, and I have to make sure that we have VLAN 200 in the what is this network? Switch 3. This is switch 3. Show VLAN ID 200. Okay, I have VLAN ID 200, and this is active, and ports are all ports on this switch. Good. Okay, I don't have to create VLAN if it show MST, show spanning tree, MST configuration, and I have VLAN 200 for even numbers and 204 for odd numbers. Yes. Okay, here MST MST configuration. There is show MST, show spanning tree, MST. I think switch 2 is our root for our region. Show spanning tree, MST. Yes, this is switch 3. C. Switch to original root. Switch 4, 3. One and 4. Okay, switch 4. Regional root is this switch 4. And there is regional root switch 4. And this is our page. Okay. Okay, now let's configure. Switch 4. We need switch 4 here and switch 3. R9 and R10. Okay. I have to create a new link R9 and switch 3 and use this IP address. Let's start by switch 3. I have VLAN 200. Okay, good. Oh, okay. Let's create enterprise VLAN. So, config T. Interface VLAN. I'll call it 200. IP address should be 156.200 and Y is router number. One 56. $200. 239, and this is switch 3. Switch 3 is 23. I have to create 24-bit subnet mask. And no shot. Okay, on R9. Show IP interface brief. This interface. Okay, I will use sub interface of 200 here. Config T interface 0/0 sub interface of 200. Because when I'm using sub interface, I have to use encapsulation.1q either. Encapsulation.1q and a special VLAN ID, which is 200. And specify IP address 156.200 39 no, and this is 3. Excuse me, 9. 39. تفاوت. Not shot. Looping. On 23. This is to show interface brief. Okay, I have configured on interface. There is no 0/0, only /1. I have configured on interface. I have to fix this one. I have to fix this one. There is no interface. No interface. This one. It's not permitted. Okay, it's upgraded. interface Ethernet 0/1 put dot after VLAN, and I have to create encapsulation.1q VLAN 200 and specify IP address 156 200 203 239 and 9 and not shut and do show IP interface brief and this interface is up and up. Let me ping do ping 239 and 33 and this work. Okay, this is this part. Concurrently between 10 and switch 4 with our path of this one use. I have to VLAN 201 for I have to VLAN 201 between 10 and switch 4. And 1 here and 200 here with the same process between 10 and switch 4. Let's start by switch 4. Make sure that I have to make sure I just have to make sure I have VLAN 201. Show VLAN. I did 201. Good. I have this VLAN. And show spanning tree MST MST configuration and region 4. I don't have an instance yet, so only instance 1. Okay, I have the VLAN. Okay, good. Let's create an interface VLAN. Config T interface VLAN 201. IP address 156 201 124 24 no shot Let's create an R10. I have to create a sub interface of 201 under this physical interface. Config T interface dot sub interface of 201 tab encapsulation dot 1q on 201. Create an IP address. One 56, 201, 124, and 10. And no shot. And for duping 24. I'm working. Okay, this is this part. This is done. You can go VIF VPN on 9 and 10 and assign these new links into VIF. I will use new VIF command, VIF definition. VIF definition is using it has address family for IPv4 and IPv6. I have to create VIF and assign this new link to these two links. I have to assign these two links into VIF by assign it by VIF forwarding command. This VIF forwarding will assign interface to VIF. VIF definition is creating VIF and VIF forwarding person. Okay, let's do this on 9 and 10. I start VIF for I think I have already VIF to show VIF. Okay, VIF definition. I have to type VIF. VPN, excuse me. VPN, I have to create VPN. VPN. And address family IPv4. I have address family IPv4. And this is good. And let's go assign this to show IP interface brief. Okay, before I assign this into VIF, let me copy this IP address because it will remove IP address. This is deleted. I have to have this IP address. The interface. Copy this address. VIF forwarding and it's called VPN. Address is removed. I have to type address again. 245.245.0 on shot. Check to show VRF VPN, and this interface is assigned to this VRF. Okay, let's do on 10 to show IP interface brief. Interface this one. IP address of this. Excuse me, I have to check this IP address. Then it's assign VRF forwarding of VPN. We have to create VRF first. VRF definition VPN address family IPv4 exit interface VRF forwarding VPN and IP address of this one. Okay, this is done, and use would distinguish a variable. This is the same as ASN I explained before. This is ASN colon NN. This is our ASN loopback 0 and 1 is for each VRF. Okay, let's go on the VRF definition VPN and type RD. ASN should be loopback 0 address. Let me do show IP interface brief. Loopback 0 is 9999. I type RD 9999 and colon 1. This is for R9 and for R10. VRF definition VPN RD 10 and 10 colon 1. Let's verify to show VRF. I have this interface on the VRF, and this is our root target address. And do show VRF. This is our interface, and this is our root target. Oh, excuse me, root ID address. Router-ID for this and Router-ID for this one. This is done. One last part, configure OSPF area 200 between 9 and switch 3 and area 201 between 10 and switch 4. Okay, I will use this process ID of 200 and process ID of 201 for this. If I see this topology, between nine and switch 3 we have 200. This 2 are OSPF area 200 and these 2 are in OSPF area 201. This is our topologies. Well, let's create our OSPF. I will use interface level configuration. Okay, where is my routers? For it is so simple, under interface level configuration, I will tap OSPF. I have to go on switch 3, I have to go on the interface VLAN 200. Okay, I'll go interface VLAN 200 and type IP OSPF process ID. I will the same as number and area is 200. This is done. And if I do show pipe section router OSPF, I can see this command. I type router ID. I'll specify router ID. These two back. I am going to hardcode this router ID into OSPF. Let's go on R9. Yeah, I have to go on this interface. Just same as this IP OSPF 200 area 200. To show on pipe section router OSPF. Okay, if you now see OSPF configuration on R9, it is router OSPF 200 and VRF VPN. This is like address family. This is something like address family. Okay, then let's go on. I'll go here. Router-ID 99999. We don't have to reload this interface later. OSPF process. Okay, show IP OSPF. Just name it. Show IP OSPF. OSPF. Name it. Okay, free we have this neighbor and full on this interface. Okay, let's configure R10 and switch 4. Here, do show IP interface brief. I have to go under this interface IP OSPF person 201 and area 201 and do show IP do shut on 5 section with OSPF and hardcode this Router-ID is 24, 24, 24 and 24. Let's go on the 10. Do show IP interface brief command, and on the interface this one. Same command. Second, yeah. And do show on pipe section with OSPF command on the this Router-ID 10, 10, 10 and 10. Okay, this Router-ID is by other process. Okay, because I have OSPF process of ID of 1, and I can't use this Router-ID again for this OSPF. Do show OS neighbor. And I have this neighbor. Okay, well, because let me have different, as I explained before, I have different OSPF process IDs on same road on 10. They all have its own separate English state databases. Okay, let's show this one. Show OSPF database. I think I can select which process ID I want. Okay, now I have one database for this 10. This is process ID of 1, and I have another database for process ID of 2. This is another OSPF database, and to make this both OSPF to see each other, I have to do redistribution. This is more important to understand. Each OSPF ID has its own database. Each OSPF process ID. Then I have to redistribute this OSPF process IDs so that each other can see each other networks. Okay, that's it. This was INE Foundation Lab 2 section 7.2. I hope you have enjoyed this video, and thank you for viewing.